So in the previous mini lecture, we asked how do you tell if your distribution is normally distributed. We saw the built-in visualizations such as QQ norm and QQ unif that we've been looking at all semester to get a quick visualization to see if a data set is normally distributed. And we looked at one of the many statistical tests that you could use, the KS test, to get a p-value for the null hypothesis that your distribution is normally distributed. And we said that often, if the data are mostly normally distributed, the t-test actually probably does fine. But what if your data is just wildly not normally distributed and you don't feel comfortable using the t-test? So there's a number of things you can do. You can try and transform your data. So you can run the t-test on the log transformation, the square root, the cube root. There's the arc cosine transformation. There's many transformations that people will use to try and take a non-normal distribution and make it more normal distribution. But an alternative is to use a non-parametric test. And I have to say the Wilcoxon test is one of my favorite tests. It's probably my go-to first test for most paired assumptions for most paired tests for most, excuse me, not necessarily paired tests, for tests that are comparing two samples. The Wilcoxon test is the test that I want to be able to make work before any other test. Like other non-parametric tests, it does require a somewhat larger sample size than parametric tests, but anytime I can use a statistical test that has fewer assumptions, I'm all for that test. So the Wilcoxon test is a really good test to have in your arsenal of tests. And like most, but not all, non-parametric tests, the Wilcoxon test works by replacing every value by its rank. So to look at the advantages and disadvantages of the Wilcoxon test, consider just a made-up data set. You have 3 blue whales with weights in the high kilograms, and you have 3 mice with weights of 10 to the minus third kilograms. And these data are completely made up. I actually have no idea what the weights of blue whales or 3 mice are. So if this offends you because the data are too far off, you can just say 3 really big things and 3 really small things. So we have a null hypothesis that the weight of the blue whales is the same as the weight of the mice, except for sampling error. Right, and so that null hypothesis you can reject with a really small p-value, even though the sample size is only n equals 3 in conditions. But this p-value is subject to the assumption of normality, and with really n equals 3 in each case, you can't really necessarily tell if your data are normal. Right, so the t-statistic is working to simplify a little bit by thinking about fitting one normal PDF to these data, another normal PDF to these data, and then asking what's the probability that these 2 probability density functions really could come from the same probability density function. This is a simplified explanation of the way the t-statistic is working. What if you don't think the data are normal? What if you think this assumption of normality is not correct? What can you do? So the Wilcoxon test replaces each value by its rank. And you can think of this as replacing an unknown distribution with a known one, right? And so once values have been replaced by their rank, we can ask what are the odds that we see a separation as good as the separation that you did see. So this is actually a calculation we can do pretty easily by hand, just using our knowledge of the choose function from earlier in the semester, right? So basically, if we replace these by rank, the 3 heaviest things are the blue whales, and the 3 lightest things are the 3 mice. Right? So we know that there's 20 possible ways, 6 choose 3 possible ways to arrange these 6 numbers. So there's only for a one-sided test, there's only 20 ways that you could separate the numbers. So there's only a 1 in 20 chance that you would get a separation as good as this by chance. So the p-value for a one-sided test is going to be 0.05, or for a two-sided test is going to be 0.1. So we can do this by hand for this simple problem, but of course it gets more complicated if you have interleaving of the ranks. So R will do this for us if we type the Wilcoxon test, right? And so I have my whales and my mice, and I say Wilcoxon test AB, and the p-value comes back as 0.1 for a two-sided test, or 0.05 for a one-sided test. You can also, the Wilcoxon test is in SciPy. There are implementations in Java as well. You do have to be careful that the Wilcoxon test actually in SciPy is using an approximation to the Wilcoxon test and requires a large sample size, and you have to be careful about that if you're using the SciPy implementation. So the Wilcoxon test has all of the options that you would expect in R. You can make it two-sided or one-sided, and you can also make it paired to test the null hypothesis that there's no change, for example, in longitudinal sampling in mice or in human samples. So in some ways, given that the Wilcoxon test is one of my favorite tests, I'm giving it fairly short shrift here and covering it fairly quickly. So that it has a big advantage and it has a big disadvantage. So the big disadvantage is there are no parametric assumptions about normality. Notice that you have not lost the assumption of independence. So there's no assumption of equivariance. There's no assumption of normality. The assumption of independence is still there. So our most subtle and difficult to understand assumption requirement for this test is still there for the Wilcoxon test. The disadvantage is also a big disadvantage is that you lose power, especially for small sample size. And this is often a big deal in genomics because in genomics, we not only have to get p-values below simple thresholds of 0.05, we also, as we saw in the previous lecture, need to correct for multiple hypothesis testing and get below Benjamini and Hochberger Bonferroni corrections, which where the effective p-value that we need to get is often much smaller than 0.05. So the loss of power by the Wilcoxon test for genomics experiments can be really serious. So in general, though, if you think your sample sizes will support it, the Wilcoxon test is a really nice test to use because you don't even have to worry about the assumption of normality. And as I said, when comparing two samples, the Wilcoxon test is often the first test that I will reach for. It is a surprisingly robust and useful test. And even though we're covering it very quickly, it should be one that you should be very comfortable using in R by just typing wilcox.test.